Welcome back, guys. Today we're going to be doing further mechanics, May June 2020, paper variant 2, which is the same as paper variant 1. Right, so let's start this thing off. Right, so the first question is on projectile motion. Okay, really easy. Particle P is projected with speed u at an angle 30 degrees above the horizontal. So I would seem it would look something like this: 30 degrees. Speed u, okay, above the horizontal from the point O. Okay, I'm gonna label this point O on a horizontal plane that moves freely under gravity. The particle reaches its greatest height at time t after the projection. Okay, and find in terms of u the speed p at time 2/3t after projection. Okay, let's consider this to be the floor. Okay, so what actually happens in projectile motion is when you throw an object with velocity like that, okay, it will reach like this. This is called your peak or the apex, and then it just falls back down in that same trajectory. It will fall back down like that. Okay, so right here is exactly the midpoint of the journey. So if this whole distance is r, at r/2 you will get this midpoint. Okay, and yes, that happens exactly at exactly half the total journey, meaning that if this was in flight for 5 seconds, exactly at 2.5 seconds it will reach this instant it will reach the peak, and it's exactly horizontal, half the horizontal distance it travels. Okay, now with that said, it reaches its greatest time at height time t after projection. Okay, now here's an important part that you gotta know. Okay, let's say that this is the particle. It would be moving with velocity u cos theta or u cos 30 degrees. I'm going to call it theta, okay, just to avoid any kind of confusions. And it would be moving upwards with a speed of u sine theta. Okay, and as such we're going to be solving it now. So as you can see, the peak, right, there's a formula for this. Now at the peak you should understand that there is no acceleration, no vertical acceleration at that point. Like, you will not consider it to be accelerating, even though it is. So u sin theta, it remains to be 0. Okay, at this point it's only been decreasing acceleration, and then it increases deceleration like this. So if I was to draw a projectile motion curve, it would have high accel here, it will keep decreasing, then it will become 0 over here, and then it will decreasing acceleration like this. So like this, it will keep decelerating at higher and higher rates. So when you first threw it, it had the most accel, then it's going up, down, and then it moves even greater with downward velocity. With that, we're going to be solving this now. At this point, the velocity is 0. So we can use the v equals to u plus at equation. So v, which is 0, equals to u sin theta, which we're only considering the vertical velocities. And since u sin theta is in the upward direction, we consider the acceleration to be negative g times t. Now t is your time t, so like this. And if we rearrange, we get t equals to u sin theta over g. Okay, now we can plug in the 30 degrees here, and u sin 30 degrees is 1/2u, so you get u by 2g. Okay, so now that we have got u by 2g, next we're going to try finding the speed of p at time 2/3t. So at 2/3t, it will be 2/3 times t. T is u by 2g, so u by 2g. We can cancel this out, and we'll be getting u by 3g, which is equal to 2/3t. Okay, nothing too confusing as of now. Now if we were to find the velocity, we would once again be using the equation. Now let's find the vertical velocity at this instant. V equals to okay, u sin theta u sine theta minus g times 2 by 3t. 2 by 3t is u by 3g, and we can cancel the g's out, and we'll be getting u by 2 minus u by 3, and the result of that is u by 6. Okay, so we know that the vertical velocity is u by 6 at the instant when t equals to 2 by 3t. The vertical velocity is u by 6. What happens to the horizontal velocity? Well, the horizontal velocity remains same all throughout projectile motion because we're not considering drag or air resistance, and horizontal velocity is u cos theta. Cos 30 degrees is, I think, root 3 by 2. Yeah, it's root 3 by 2, so it will be u root 3 by 2. Now this isn't finished yet because they're telling us to find the speed of p, not the vertical speed, not the horizontal speed, the speed, and the speed is just the resultant vector of the two. This is going to be a speed. Okay, let's call that v. We'll call this vy just for lesser confusion, I guess. Okay, yeah. So if we want to find v, we can use, since it's a right angle triangle, we can use hypotenuse. You can use the hypotenuse thing. So v square equals to u root 3 by 2 the whole square is 3u square by 4, and we're gonna add that with u square by 36. Okay, so upon adding it, we would be getting okay, wait, let me just add that right now. So we would have to multiply this by 9, so this will be 27u square plus u square divided by 36, which is equal to 28u square by 36. Okay, so 28u square by 36 equals to, now we can divide 4 on both sides, we get 7 by 9u square, and this is equal to v square. So when we root both sides, we'll be able to get v. So v equals to root 7 over 3u. This is the speed of v. This is the final speed at time t equals to 2 by 3t. Okay, nothing too complex as of now, but that's projectile motion. Okay, we got circular motion now. And okay, first show that cos theta equals to 1 by 3. Fine, so I would normally start off by labeling the diagram. Okay, so yeah, a light inextensible string of length a is threaded to a fixed smooth ring r. One end of the string is attached to a particle of a of mass 3m, so I'm going to label this as 3mg. Okay, other end is attached to a mass m. I'm going to label this mg. Okay, the particle A hangs in equilibrium at a distance x vertically below the ring. Okay, so if this is x and the whole length of the string is a, I can say that this is a minus x. Okay, let's call that a minus x. We don't need to assign another variable. Okay, the angle between AR and BR is theta. Okay, that's shown. Particle B moves in a horizontal circle with a constant angular speed 2 root g by a. Okay, I'm not going to label that, but I will denote that as omega. Okay, this is angular velocity or angular speed, it doesn't matter. Show that cos theta equals to 1 by 3. Okay, fine. So how would we do this? I would initially start by resolving the forces. So let's use a different ink. Okay, now since we have two particles, we can model it into two different systems. The first system can be this right here, and the second system can be this right here. This is the second system. So let's evaluate the first system. Okay, we can see that there will be a tension. Let's erase the second thingy. Yeah, so you can see that there will be a tension in the string that is opposing the motion of it going down. If it's in equilibrium, there must be a tension upwards so that it doesn't fall, right? And there should also be a tension in the string this way such that this doesn't fall down either. And you should understand that the tensions are equal all throughout the string, okay? Meaning that the tension over here is equal to the tension over here, okay? But that doesn't mean they have the same effect, okay? Because if you pulled something with 10 newtons, when it's like this, if you pulled it with 10 newtons like this at 30 degrees or at theta degrees, the effective force is basically 10 cos theta. This is the actual force you're putting on the object to move horizontally to the left. However, if I push it 10 newtons this way, that would mean that I'm actually pushing it with 10 newtons. In that similar understanding, tension is directly acting upwards like this, so it's having maximum effect. Meanwhile, it is acting at an angle theta over here to, having a little bit of a minimal effect. But regardless, let's first resolve the forces. So looking at the first system, you can see that there's a force T upwards and mg downwards. And since the entire system is in equilibrium for particle A, it means that the forces are equal, meaning T equals to 3mg. Right, perfect. Now for this one, you can see that it hangs at mg. So let's consider the vertical forces here. Now tension is not a vertical force. In fact, it has a vertical component. Okay, and that component can be found easily. Think about it this way. Let's draw a triangle. Let's complete this triangle. Let's use the black ink. Yeah, now think about it as a triangle now. Let's say you completed the triangle. Okay. Tension's acting this way, angle theta. Remember, I'm just simply mirroring what's shown over here. Okay. Now, tension's forces, meaning if it's going from here to here, there must be forces like this. It's how you draw a vector. This would be T sine theta. This would be T cos theta. Okay, now what does this tell me? The vertical component of the tension, T cos theta, equals to the vertical component acting downwards, mg. Now, what do I know? T equals to 3mg, and I told you tension remains same all throughout. It's simply the effect changes. So 3mg cos theta equals to mg. And now we can resolve the forces. So I mean we can arrange it to the different sides. So cos theta equals to mg by 3mg. We cut the mg's out, we get 1 by 3. And that's how you solve the first part of the question. Moving on to the second part, going back to blue, moves in a horizontal circle. Okay, now until now we've dealt with systems that are in equilibrium. 3mg is in equilibrium vertically, it is not moving horizontally, so it's fully in equilibrium. B is vertically in equilibrium, but horizontally it is not, for it is moving in a circle. So the resultant force, let's find that out. So what are the forces acting on B? mg is there, and then there's a tension in the string. Okay, now what makes it move horizontally? What's the force that makes it move horizontally? T sine theta. Okay, the tension's horizontal component makes it move in a circle. And we also know that T sine theta is called your centripetal force. Okay, what the resultant force of all the forces acting on B horizontally make up your centripetal force. As such, we can say that T sine theta equals to mr omega square. Mr omega square. This is another formula for the centripetal force. Right. Okay, now from here on it's simple. We can rearrange. So T equals to 3mg, and if cos theta equals to 1 by 3, sine theta must be 2 root 2 by 3. This is sine theta. You can use the sine square plus cos square equals to 1. So yeah, using that identity, we can say that this is 2 by 3, and this is equal to mass times the radius. Now radius, let's leave that right now. We don't know the radius of it revolving, right? The radius right here, let's call that radius r. okay, and we times that with omega square. Now omega square is, well, this is omega, so squaring that would give me 4 times GA, right? 4 times GA. Okay, now let's well, arrange some stuff. 2 root 2 mg, I cancel the 3 out here and here, equals to mr 4 mr g by a. I should have wrote mgr, but it doesn't change much. Okay, now mg gets cancelled here, m gets cancelled here, here. So what I'm remaining is 2 root 2a equals to 4r, and we can rearrange that with 2 root 2a equals to 2r, and so r equals to a root 2 over 2. Okay, is that the remaining? No, we need to find x in terms of a. Now you should understand that the radius is this side, x is, well, this length here, and the whole length of the string at this instant would be a minus x. Okay, and we know that it's an angle theta. Now what does this tell me? The opposite side, and we have the hypotenuse side fully completed. We don't have this side completed because it is, well, x only extends to this much. We don't have the remaining side here. Okay, and as such we can use the opposite and hypotenuse. So sine theta equals to the opposite, which is the radius, divided by the hypotenuse, which is a minus x. And I told you sine theta equals to 2 root 2 over 3 over 3. Now we know r equals to a root 2 by 2, so let us write that down. A root 2 divided by 2 times a minus x, and that is equal to 2 root 2 by 3. Now I'm going to cancel out this root 2 over here and here, and we can cross multiply. We get 3a equals to 4a minus x. Expanding the brackets, we get 4a minus 4x equals to 3a, and now rearranging it, we get 4x equals to a. So that means x equals to 1 by 4a. That's how you would solve this question. Overall, it's a really simple question, but it just requires you to understand and, I guess, not panic during the situation. But it's quite easy to solve. Right, now let's proceed. Show that the initial acceleration of p is 3 by 2g upwards. I like reading the question first. Okay, one end of a light elastic spring of natural length a modulus 5mg is attached to a fixed point a. The other end of the string is attached to a particle p of mass m. Okay, the spring hangs vertically with p vertically below a. Okay, I'm assuming this is just a vertical spring then. Okay, p is released from rest in the position where the extension of the spring is 1 by 2a. Show that the initial acceleration of p is 3 by 2g upwards. Okay, fine. So the first step I would do is to draw a diagram. That's exactly what I'm going to be doing. I will consider this to be like a sort of ceiling. Okay, now whenever I'm drawing springs, well, let me first label this as a. Yeah, whenever I'm drawing springs, I like to draw it as zigzags, so like this. I think this is the common convention used for springs. Okay, let's draw it as zigzags, and let's say that we are attaching this is particle p, and it has a mass m, so force mg this way. Now one thing you should know is that for springs there is always a tension, okay, in the spring. So when you compress a spring, there's an equal tension as when you extend the spring by that same amount. Now let's label the diagram for a bit more context. This would probably be a, and it is hanging where the extension is 1 by 2a, so this is 1 by 2a. You should always understand that whenever you extend a spring, there's a tensile force trying to bring it back to equilibrium at the natural length a. So there will be an upward force this way. This is going to be called T. Okay, and it wants to just go back to natural length. That's the main mission of this force. In the similar manner, if I compressed it by 1 by 2a, there is a force acting downwards to bring it back to this equilibrium point of the spring. This is what it wants to reach. Now let's proceed with the calculations here. There's an upward force of T, there's a downward force of mg, and because of this, the particle of mass m will accelerate like this, F equals to ma. Now T can be denoted by using the formulas. So T equals to modulus x by L, modulus being the modulus of elasticity, lambda. So phi mg multiplied by 1 by 2a divided by natural length a. So we cut that, we get phi by 2 mg. So now let's go bring this back to our main equation. Phi by 2 mg minus mg equals to ma, and doing this gives me 3 by 2 mg. Now I can divide m on both sides. I get a equals to 3 by 2 g, and this is acting upwards because we considered t being like that. So that was an easy question. A lot of working space, don't know why. Find this. Okay, now we're supposed to find the speed of p when the spring first returns to natural length. Okay, interesting. Yeah, this is quite an interesting one. Okay, well, there's an easy way to solve this. You should understand that energy equals to the kinetic energy at a point. I write I as an initial energy plus gravitational potential energy at the point, initial, plus elastic potential energy at the point, plus work done by friction initially. And this is equal to the final energy of the spring. Remember, energy is conserved, and this is the final energy. So taking any 2 points, this result should be giving me what I want. Okay, now it says that they release from rest in the position where the extension is 1 by 2a. So let's consider all the forces, all the energies acting on the spring at exactly 1 by 2a. Going back, let's understand this now. When x equals to 1 by 2a, remember the x means extension, we can use this entire thing. Okay, so let's write that in blue ink. So the initial energy, let's consider this to be the initial scenario. Remember, the final scenario is when it returns to natural length, basically when x equals to 0. So the initial scenario we can take as 1 by 2a. Kinetic energy, since it is released from rest, we can say that kinetic energy is 0. Zero kinetic energy. Now gravitational potential energy, let's consider 1 by 2a as the baseline, okay, and anything above it to be positive GPE and anything below it to be negative GPE. Meaning if we consider this to be the baseline, the change in GPE will be positive if you go upwards, positive, and if you go downwards, the change in GPE will be negative. So essentially this point has 0 GPE. That's what we're trying to say. Yeah, and according to, we're going to say that it has 0 GPE as well. Elastic potential energy is modulus, I will write the formula, modulus x square by 2L. I like saying modulus instead of lambda, but don't know why. And work done by friction, since there is no mention of any friction, we're going to say that's 0. So let's solve this. And this is equal to the energy when x equals to 0. Energy finally, x equals to 0. Okay, now let's solve. Lambda equals to 5 mg, multiply that with the extension, which is 1 by 2a, the whole square, whole divide that with 2 times a. That will be giving me 5 by 4 mga square divided by 2a, which is equal to 5 by 8 mg Ga. Okay, this is my initial energy, Ei. Now let's work out the final energy. Going back, now let's write the formula for finding the final energy. Ef equals to kinetic energy finally plus gravitational potential energy in the final stage plus elastic potential energy plus work done by friction final. Okay, and this is equal to the initial energy, which is equal to 5 by 8 mga. Okay, now it's easy from here. The kinetic energy, you're supposed to find the speed of p when it first returns natural length, which is basically a. We need to find the speed of p. Let's call that v. Okay, so kinetic energy will be called half mv square. Okay, energy F equals to half mv square. GPE. Okay, now when it returns a natural length, we can see it moves 1 by 2a positive 1 by 2a since when it began. So the change in height equals to 1 by 2a. We know GPE is measured by mg delta h, so plus mg times change this one 1 by 2a plus the elastic potential energy at that instant. Okay, I'm going to write down the calculation like this: 5 mg times, now when it returns natural length, x equals to 0, so x times 0 square by 2a. Basically this becomes 0, and the work done by friction, once again no mention, so yeah. Now rearranging it, not rearranging it but simplifying it, half mv square plus half mga equals to 5 by 8 mga. Now if I bring this towards the right hand side, I get half mv square equals to 1 by 8 mga. I can cut the masses on both sides. I can multiply both sides with 2 to get v square equals to 1 by 4 ga. And now I can use the square root. V equals to root of 1 by 4 ga. And yeah, 1 by 4 can be rooted as 1 by 2. So I'm going to write this as 1 by 2 root ga. This is the final velocity when it reaches that spring, when it reaches natural length. Okay. Yeah. Moving on. Okay, equilibrium. Equilibrium is a really easy chapter. There's a very simple way to solve this. Okay, so you don't need to read the question most of the time, but for the sake of it, I will read it. Uniform square lamina ABCD has sides of length 10 centimeters. Okay, so I'm going to label this as 10 minus x. This is going to be 2.5. This is 10. This is 10. Okay. I think I can make that a bit visible. Yeah. The point E is on BC, with EC being equal to 7.5. The F is on BC such that CF equals to X. Triangle is removed from ABCD. The center of the mass is a distance x mean from CB and y mean from CD. Okay, basically we're trying to find the exact center of mass. Let's call this the center of mass, and its coordinates are x mean, comma y mean. Okay, now x mean is basically the horizontal distance from the vertical axis, and y mean is basically the vertical distance from the horizontal axis. So if you want to show x mean equals to this, how would we do it? Firstly, the very first thing that you should do is make a table. So we start off by labeling the shapes that we have. We have a big square, we have a triangle cut out, and we have the shape ABFD, the whole thing. So let's start off with the square. I'm going to call it SQ. Next, the triangle. I'm going to just label it as a triangle. And then there is ABEFD. Yeah, ABEFD. Okay. Now there are three things that you need to consider when you're doing area based calculations. Firstly, it's area whenever it's 2D laminars or something, and you're not dealing with volumes. Secondly, we find the center of mass from the vertical axis. So I would write this as COM from BC. And then the third thing would be the center of mass from CD, the horizontal axis. You can, flip-flop this around, it really doesn't matter. But first let's find the area of the square. It is 10 times 10, which is 100 centimeters square. 100 centimeters square. Okay. Area of the triangle, it's going to be half times the base times, this can be written as 15 by 2. So we get 15 by 4x centimeters square. Does that work? Yeah, it does work. So I'm going to write this as 15 by 4 x centimeters square. So ABFT, area square minus area of triangle. So it'll be 100 minus 15 by 4 x. Right. Moving on, let's do center of mass from BC. So for a square, you should understand that for a square, the midpoint is the center of mass. So if I have a side x like this, x by 2, comma x by 2 will represent my midpoint. In our case, we have x equals to 10. 10, 10, 10, 10. So midpoint is 5, comma 5. So the center of mass from BC is 5 centimeters. Center of mass from CD will also be 5 centimeters. It's just the vertical and horizontal distance from the two edges, from here and from here. Okay. Then what about the triangle? For a triangle, it's a little different. Okay, if you have something of length y and length x, the center of mass G will be such that it is 1/3 of the horizontal distance and 1/3 of the vertical distance, meaning x by 3 comma y by 3. And as such, we will do that. Our horizontal distance is x by 3, that's right here, x by 3, and our vertical distance is 7.5 divided by 3, so somewhere about here, and that's going to be 2.5. So now I'm going to write this as 2.5 centimeters. You can write this as 5 by 2 also, it doesn't really matter. Let's write that as 5 by 2. And the center of mass from BC of the entire shape ABEFD is x mean, which is what we're trying to find out. And center of mass from CD or DC, whatever, is going to be called y mean. Okay, now to find this, it is very simple. We have to use a few principle of moments and all that stuff. So yeah, we can use the force law, F equals to ma kind of laws. So this is 100 area of the big shape, and then we minus that. So basically what we're trying to do is find the moment caused by the first shape, and we subtract that with the area that's cut off, the moment caused by the area cut off. So let's resolve for x mean first. Okay, if we are considering all the horizontal moments that cause the shape to have an x mean, we're going to say it's 100 times the center of mass from BC, which is 5. Okay, so a positive 100 times 5 is the moment that's created. But whenever we're dealing with areas and all that stuff, we include another term. We can call it sigma, or we can call it rho. I would like to call it sigma, but this is a form of density. This is what we write. Okay, it is an essential factor, and we subtract that. Why do we subtract it? Because this shape is cut off. Okay, so what this entire square, this square over here, it creates a positive moment. Positive. Okay, But this triangle over here, since it is cut off, it creates negative moment. So resolving all the moments, we get 100 times phi times sigma minus 15 by 4 x times sigma times 5. Times x by 3. And that should be equal to the overall moment caused, and that's going to be 100 minus 15 by 4 x times sigma times x mean. This gives me 500 sigma, and this will give me 5 by 4. I think this will give me 5 by 4 x square sigma, and that is equal to, let's not expand it just yet, 100 minus 15 by 4 x times sigma x mean. What do I see here? This sigma can be cut off, this sigma can be cut off, and this sigma can be cut off. So I'll write this as 500 minus 5 by 4 x square. Now we divide that. Okay, let's bring this term this way. So we divide that with 100 minus 15 by 4x. Do we have more space? I cannot load. And yeah, now that's equal to x mean. Now if we multiply everything by 4, we get 2000 minus 5x square by 400 minus 15x. Remember, all I did is multiply the numerator and denominator by 4. Now let's divide it with 5. I get 400 minus x square divided by 80 minus 3x. And you can see that this is what we want right here. Now to find y mean, we do the same process, just a bit different. So let's find for y mean. For y mean now, 100 times phi times sigma, that remains the same, minus 15 by 4 x sigma times 5 by 2, because now we're considering the verticals. So 5 by 2, and that let's simplify this first. Now that's 500 sigma minus that with minus that with 75 by 8 x sigma, which is equal to 100 minus 15 by 4 x sigma y mean. Okay, now once again, this is the area of the whole shape. That's what I'm doing. Let's cancel out the sigmas. Let's bring this to the denominator. So we get 500 minus 75 by 8 x whole divided by 100 minus 15 by 4x. Okay, and that's equal to y mean. Y mean. Now let's multiply 8 on both sides, numerator and denominator. So numerator multiplied by 8 gives me 4000 minus 75 by x whole divided by 8 times this will give me 800, and we subtract that from 8 times this, which is 30x. Okay, so we can do that. And now let's find a common denominator as such, a common factor, and then we can divide it overall. So dividing this by 5 gives me 800, and dividing this by 5 gives me 15x, and we divide this by 5. Dividing 800 by 5 should give me 160, and dividing 30x by 5 gives me 6x. Right, I think this is what they'd be expecting of us, to get 800 minus 15 x divided by 160 minus 6x. Yeah, I think this is it. Okay, yeah, so x mean and y mean really easily solved. Now what do we have here? Shape ABEFD is in equilibrium in a vertical plane with edge DF resting on a smooth horizontal surface. Oh, okay, so if I was to draw that, I will now use the blue ink. Yeah. So if I was to draw that, it would mean like this. This is D. Sorry, this is F, and this is D. Okay, so it is resting like this. Find the greatest possible value of x and give it in the form a plus this. Oh yeah, and this is x. Okay. Now here's an interesting part. Consider this. This is a can. Okay. Right now it does not fall. Okay. The moment I tip it like this. Okay. If the center of mass is right here, do you think it will fall? Well, we need to check. We first consider the baseline. We consider the point that's tipping off. It's supposed to be vertical, but since the center of mass has not crossed this line, okay, if you look at this real carefully, we can see that the baseline is like this and it's like this. Since the center of mass is within the baselines, it will not fall. But the moment I tip it like this, while center of mass is here and while the baselines are right here, it will not tip off because it is outside, so it's now going to fall down. In this one, it's just going to come back down like that. In that same way, the x mean and y mean, this is the baseline. This is one baseline, this is the other baseline. X mean needs to be within this line. Okay, so which is overall 10. This must be x, and x mean must be within this line, within this. What does that tell me? It tells me that x mean must be greater than x. If x mean becomes lower than x, that means x mean would be residing in this region right here, and that means it would fall because it is outside the center of mass's baseline. And we can use this inequality to solve it. It can be lesser than or equal to. Okay, that is lesser than, it will fall. So what does this tell me? For it to be in equilibrium, x mean must be greater than or equal to x. The moment x mean becomes lower than x, it will fall into this region and it is going to fall down like this. So let's solve this. X mean was 400 minus x squared divided by 80 minus 3x. 400 minus x squared divided by 80 minus 3x, and that must be lower than, no sorry, greater than or equal to x. Yeah, it must be greater than x. So I can rearrange the inequality. I get this, and then 80x minus 3x squared. I can divide both sides by 2 and then I can rearrange it. Well, let's first rearrange it. 2x squared minus 80x plus 400 is greater than or equal to 0. We can divide 2 on both sides. We get x squared minus 40x plus 200 is greater than or equal to 0. Okay, now let's solve this quadratic. I'm going to input this into my calculator. 1 minus 40, 200. Okay, so my two values for x are x equals to 20 plus or minus 10 root 2. Now here's an interesting point. Okay, 20 plus 10 root 2 equals to 34.14. 20 minus 10 root 2, remember we have to consider both possibilities, equals to 5.86. Normally we consider positives for anything regarding measurements, right? Because you cannot have a negative side. But in our case, our answer is the negative. Why, you may ask? It is because the square is of side length 10. X makes up a portion of the side length 10. This tells me that x must be definitely lower than 10. X is definitely lower than 10. X cannot be greater than 10 because then x would be somewhere like this. this should be x. Since x is a part where CF, where f is on DC, x must be lower than 10, and as such 20 minus 10 root 2 is going to be a value of x, and that is exactly how they wanted it to be. Alright, so equilibrium solved. Now we got linear motion under a variable force. Okay, P is moving along a straight line with acceleration 3ku minus kv, v velocity, t equals to t, time equals to t, u is initial velocity, and k is constant. The velocity and acceleration of P are both in the direction of increasing displacement. Okay, the first thing I understood from this is that u equals to v, or v equals to u at time t equals to 0. If you're asking why, initial velocity is when t equals to 0. The initial velocity equals to the final velocity when t equals to 0. Okay, because when you're using v equals to u, if you're using v equals to u plus at, if you're using this relation, you'll understand that if you put t equals to 0, u equals to v. This is an important condition. Okay, let's start off. Find the time taken for P to reach a velocity of 2u. Okay, fine. So it says acceleration is this. Acceleration I write it as dv over dt, and that is equal to 3ku minus kv. Now there's an important thing to understand. Whenever we are doing these kind of stuff, we need to make sure that dv is coupled with v and dt is coupled with any terms regarding t or any constant or whatever it is. So if I just did dt equals to dv over 3ku minus kv, it's done. That's it. All the terms regarding t is on one side and all the terms regarding dv is on the other side. But I think I can make my life a bit easier if I just factorized 1 by k out of this. Then I'd be getting dv times 3u minus v. I think it makes my life a bit easier. So now we have k dt equals to 1 by 3u minus v dv. Now what I can do is integrate both sides to get rid of the dt and dv. So integrating k with respect to t will give me kt plus c. Okay, remember we write the plus c for whenever we're integrating t. As for this side, you can see that this is in a form of the ln, right? Because when you differentiate ln, we use f dash x by fx. Okay, when you integrate this, you get ln f of x. That's what we're going to do here. If f of x equals to 3u minus v, then that means f dash of x should be negative 1. So if I put negative 1 over here, I need to put a negative 1 over here. Okay, so that I can cancel them out. And remember, you can factorize our constants. So we get negative ln 3u minus v. Okay, now how do we find c? This is where the condition comes in. U equals to v when t equals to 0. So saying t equals to 0 meaning c equals to negative ln 3u minus v. Okay. Yeah, so saying that gives me this, and yeah, now it's a little bit simpler, I'd say. So I would bring in negatives to the one side and solve it like that. But okay, how I would write it is, okay, instead of starting off like this, I would much rather do it as how would you do it? Okay, I would first rearrange to find v. So I get negative kt minus c equals to ln 3u minus v. Okay, what do we have next? Yeah, then I think I can do the ln and ln. Yeah, I could do that. Okay, it's an interesting question. I could rearrange it and write it as in the power of e, but I think that would cause a bit of confusion, perhaps. Okay, let's just plug in t equals to 0, c equals to ln 3u minus v. We know that v equals to u at that instant, so equals to ln 2u. It's equal to negative ln 2u, sorry, negative ln 2u. So kt minus ln 2u equals to negative ln 3u minus v. Okay, now let's write it as kt equals to, now let's bring this ln to the positive side. We get ln 2u minus ln 3u minus v, and we can write this as 2u divided by 3u minus v. Okay, and this is all ln equals to kt. I think now we can write this as e to the power of kt equals to 2u by 3u minus v. So yeah, I think we can do that. So I can write this as 2u divided by e to the power kt equals to 2u times e to the power of negative kt, and that's equal to 3u minus v. So that means v equals to 3u minus 2u e to the power of negative kt. Yeah, okay, yeah, we did that and we got this. Now find the time taken to achieve a velocity of 2u. So we've got the final equation. Now let's find the time taken to get that equation. So velocity is 2u, and that is equal to 3u minus 2u e to the power negative kt. Perfect. Now if we rearrange it, we get 2u e to the power of negative kt equals to u, because minus signs cancel out when you bring 3u this side, and yeah, we can cancel that, we get 1. So we get e to the power of negative kt equals to 1 by 2. Negative kt equals to ln 1 by 2, which is equal to negative ln 2, because this is 2 to the power of minus 1, and 2 to the power minus 1, we can bring the minus 1 outside, and we can cut the negatives on both sides. So t equals to 1 by k ln 2. This is the answer. Okay, that was to solve for t. Now the second question, find an expression for the displacement of p from its initial position when its velocity is 2u. Okay, fine. Yeah, I think that can happen. So let's write down the velocity equation first. Minus 2u e to the power of negative kt. Now if I integrate this with respect to t, let's integrate this with respect to t. Let's integrate, sorry. So if I wrote this as dx over dt, that is basically 3u minus u e to the power negative kt. Now if I integrate this with respect to dt, okay, I get x equals to, now let's integrate 3u minus 2u e to the power negative kt. Okay, integrating this with respect to dt, yeah, so we get 3u times t. This is the simple integration. Minus out with 2, we can factorize 2 out, 2u actually, and yes, now integrating e to the power of negative kt will give me negative 1 by k times e to the power of negative kt. Let me check. Yeah, it does, and we need to write plus c, obviously. 3ut minus, okay, minus gets cancelled out, so we get plus 2u by k times e to the power of negative kt plus c equals to x. Okay, fine. Now once again we can use t equals to 0, u equals to v. So this gets cancelled out. Okay, maybe not cancelled out like that. We can say that 0 plus 2u by k times e to the power of 0 plus c equals to 0, because it starts off when you start it off, x equals to 0, and so we can say c equals to negative 2u by k. I think, wait, let me see. Yeah, c equals to negative 2u by k. So now we have another equation, 3ut plus 2u by k times e to the power of negative kt. And since we have negative over there, I think we can write this as minus 1. I think it works the same way, and that's equals to x. Now we need to find x when velocity equals to 2u, v equals to 2u, and when v equals to 2u, t equals to 1 by k. Yeah, v equals to 1 by k ln 2. So plugging in those limits, this becomes 3u by k ln 2 plus 2u by k Going back to what we have here, yeah, going back to what we have here, e to the power of negative kt, that's just going to be t equals to 1 by k. So since it's going to be e to the power of negative k times 1 by k ln 2 minus 1 equals to x. So this becomes 3u by k ln 2 plus that with 2u by k, and what do we have here? Okay, so k gets cancelled out, we get negative ln 2, so that is going to be 1 by 2 minus 1. This becomes 1 by 2, and that's equal to 3u by k ln 2. If this becomes negative 1 by 2, then we add this as minus u by k. Now I think we can factorize u by k out, so we get u by k times 3 ln 2 minus 1. That's equals to x. Can we simplify it further? I don't think so, and I think this is the acceptable answer that we can use. But yeah, that's how we do it. It's just algebra, but like it could get confusing along the way. That's linear motion under the variable force. Now we have momentum. Okay, very easy, this one. Anything regarding momentum is actually very easy. So let's consider this. Okay, m moving smooth horizontal surface, vertical barrier. At the instant of impact, the direction of motion of p makes an angle alpha with the barrier. Okay, so I've got a ball here, it is colliding, it makes an angle alpha with the barrier. Then the coefficient of restitution is E. Result, it changes through 90 degrees, so it moves like this. This is 90 degrees and this is another ball. Okay, now here's an interesting part. Since all the angles in a line add up to 180, alpha plus 90 plus, let's call this beta or whatever, equals 180. This means that this is 90 minus alpha. This is going to be a massive clue. As a result, it is turned through impact. Okay, so how I would start off is that it starts off with velocity u. This tells me that the horizontal component of the velocity, if you complete the triangle, okay, if you complete the triangle and you try to find the horizontal component of the velocity and the vertical component, ux will be u sine alpha. Uy would be equal to u cos alpha. Okay, it leaves with a velocity v. We can label it as v even though the question never mentions it. So Vx equals to v times sine 90 minus alpha, and Vy equals to v cos 90 minus alpha. Okay, now here's an interesting identity that you gotta know. Sine 90 minus alpha equals to cos alpha, and cos 90 minus alpha equals to sine alpha, and as such v cos alpha, Vx equals to v cos alpha, Vy equals to v sine alpha. Now you should understand that the velocities all relate to each other. Since the collision is horizontal, okay, since the wall is parallel to the vertical velocity's direction, the vertical velocity does not change. This tells me that Vy equals to Uy. And since it is colliding perpendicularly 90 degrees, we now understand that the coefficient of restitution does in fact affect the resulting motion. So that means that Vx equals to E times Ux. So let's solve this one by one. We can start off with the very first one. Vy equals to Uy. Uy was U cos alpha, Vy was V sin alpha. So that means that U cos alpha equals to V sin alpha. Okay, from this I'm getting U equals to V tan alpha. Okay, let's leave it at this for now. Okay, now we can solve the other side. How many marks? 3 marks. Okay, we can solve the other side. So Vx equals to E times Ux. So Vx is V cos alpha, and E times U times, now x is equal to sin alpha. Okay, so I get V equals to, no, I'll write this as U equals to V cos alpha divided by E sin alpha, which means V divided by E tan alpha. Okay, is that right? Yeah, this is correct. Okay, so U equals to this. Now U equals to B tan alpha as well, so let's write this as this. We can multiply and cancel this out, so we get 1 by E. We can multiply tan alpha on both sides, we'll get tan squared alpha. This is what we originally wanted, so we're right. Moving on, particle P loses 2/3 of its kinetic energy at impact. Okay, before we even try to find alpha and E, understand that it has a kinetic energy of half mu square. Now losing 2/3, it loses 2/3, meaning it keeps only 1/3 of it. So now its kinetic energy is half 6 mu square. Okay, that's what losing 2/3 of its kinetic energy means. It keeps it becomes like that. Now if this is the final kinetic energy, you should understand that since it leaves with velocity v, that will be equal to half mv square. Now I can cancel masses on both sides, okay, and I can multiply both sides with 2, so this gives me v square equals to 1/3 u square. Important formula. Now let's move on. Okay, as a result of this, let's go back to our previous one, v cos alpha, this equation right here. Okay, v cos alpha equals to, well, okay, let me see. Okay, fine. Anyways, yeah, v equals to EU sine alpha. No, actually I think we can use this one. V equals to, let's actually erase that properly. Yeah, we know that V sine alpha equals to U cos alpha. So we can say that V equals to U cos alpha by sine alpha, and that's just U by tan alpha. We can square both sides because we're going to rearrange for V square. Squaring both sides gives me U square by tan square alpha. Okay, and that's equal to 1 by 3 U square. U square cancels out. I get tan square alpha equals to 3. That means tan alpha equals to root 3. Alpha equals to tan inverse of root 3. Tan inverse of root 3. Okay, that means that alpha equals to 60 degrees and E equals to 1 by tan square alpha. 1 by tan square alpha is 1 by 3. So it's just 1 by 3 equals 1 by 3. Alpha equals 60 degrees. That's momentum. Now for the final part, which is question number 7, usually the harder ones, but yeah. Hollow cylinder of radius A is fixed with its axis horizontal. This axis horizontal. Okay, yeah. Particle P of mass m moves in part in a vertical circle along the smooth inner surface of the cylinder. The speed of P when it's at its lowest point is root 7 by 2 GA. It loses contact with the surface of the cylinder when it makes an angle theta with the upward vertical interval. Okay. I would say this is quite an easy one, but let's start this off. Not really much of a circle, more like a rounded square, but let's consider this to be a circle. So at the lowest point, which is, I will draw that black. At the lowest point, you get root 7 by 2 GA. Yep. Radius is A, and it loses its contact when it is at with theta. I assume that it's going to rotate anti-clockwise, so we can say cancel that. We can say that this is going to be A, this is going to be theta as well. So with that being said, we can now solve this. This instant it loses contact, so let's find the kinetic energy at low point. At low, kinetic energy equals to half times mass times 7 by 2 GA, which is equal to 7 by 4 mGA. The gravitational potential energy equals to 0. We're considering this to be the baseline. Okay. Okay, now we're going to find out at high. At the high point, kinetic energy Ke equals to half mv square. The potential energy equals to mass times g times a plus a cos theta. Okay, reason being so is that it goes a, and then a cos theta gives me the remaining length to give me the actual vertical distance, so a cos theta. Now we can equate half mv square equals, plus mga plus mga cos theta equals to 7 by 4 mga. Now we can write this as half mv square plus mga cos theta equals to 3 by 4 mga. Simply rearrange it to the side. Okay, multiplying 2 on both sides gives me mv square plus mg a 2 mga cos theta equals to 3 by 2 mga. I can divide both sides with a, so I get mv square by a plus 2 mg cos theta equals to 3 by 2 mg. Okay, now I would never divide it by a, but with practice you'll understand that by resolving forces, this is a force mg, and then there's also a normal reaction force of force r. Doing that gives me r minus mg cos theta equals to mv square over a, and not minus, it's plus, because they both act in the same direction towards the center. And because of that, I know that it loses contact at this point theta, meaning r equals to 0. So if mv square over a equals to mg cos theta, I can say, now by substituting this over here, I can say 3 mg cos theta equals to 3 by 2 mg. Cancelling 3 mg on both sides, I get cos theta equals to 1 by 2, and cos inverse of 1 by 2 equals to theta, which is, let me just check, cos, yeah, it is 60 degrees. Alright, fine, so we got 60 degrees there. Show that in the subsequent motion it strikes the cylinder at point A. Okay, this is very simple. So you're telling me that its height is a plus a cos theta. Cos 60 degrees is 1 by 2, so its height is 3 by 2a. Its distance, since it's striking at point A, which is the lowest point, your horizontal distance will be a sine theta. Okay, this will be a sine theta. Now a sine theta is, well, a sine 60, which is root 3 by 2. So this is going to be root 3 by 2a. We just need to show it fulfills this trajectory. And what does this tell me? Again, keyword trajectory. So we know that it goes under projectile motion, and it's going to fall like this straight over there, and its initial velocity will be the velocity it left at, and its degree of projection is exactly at the degree with the vertical, 60 degrees. Okay, now how do we find v? Well, earlier from this equation we got mv square equals to 2 mga cos theta equals to 3 by 2 mga. Let's rewrite that again. Mv square plus 2 mg cos theta equals to 3 by 2 mg. Let me see if I wrote that right. mga. Oh right, I forgot the a's. So a cos theta equals to cos 60 degrees, which is 1 by 2. So this gives me mga over here. Mga, sorry, plus mv square. So mv square equals to 1 by 2 mga. V square equals to 1 by 2 ga. I just cut out the m on both sides. Rooting both sides gives me v equals to 1 by 2 ga root 1 by 2 ga. Okay, now if it was to travel a horizontal distance of root 3 by 2a, we know that x equals to uxt, basically the horizontal component of velocity, u cos theta times t. So its total, now let's consider total right here. Total horizontal range is root 3 by 2a. That's equal to v, we're gonna write this as v, okay? V cos 60 degrees times the total time taken, t. So t equals to root 3 by 2a divided by root 1 by 2 ga times 1 by 2. And we can multiply 2 on both sides, we get root 3a divided by root 1 by 2 ga. And we can take out the a from here, we can take it out, we get 3 over 1 by 2 ga, 1 by 2 ga, I think. Let me check that out. let's see. Yeah, and then I can write this as t equals to, I can multiply 2 on both sides. I get 6 by GA, root 6 by GA, times A. Now if I square A and then I root it like this, I get t equals to 6A by G, whole root. Okay, right. Now the vertical height, you can represent that as S equals to UYT plus minus half GT square, and as such the vertical height is actually negative 3 by 2a because it's going downwards. So minus 3 by 2a equals to uy. Now uy is going to be vy. Vy is v sine 60 degrees. So root 3 by 2 times v. I'm not going to write root 1 by 2 ga because it could be confusing. T minus half times g times t square. Let's write all the stuff that we can about t. Root 3 by 2 times root 6a by g, and I think now it's an appropriate time to include v as well, so it'll be root 1 by 2 ga. Okay, let's just evaluate this term first. This gives me whole root of, let's just square this and write it as 3 by 4 times 6a by g times 1 by 2 ga, and this is equal to the root of let's see, 18 by 8. Okay, a lot of calculations here. 3 times 6 times 4 2, yeah, I get 9 by 4. 9 by 4, g gets cancelled out here. A square, which is equal to 3 by 2a. Evaluating this term, minus half gt square, let's just evaluate it as half gt square. Half gt square equals to half times g times 6a by g. G cancels out, we get 3a, and this was root 3 by 2 vt. So doing this minus this gives me 3 by 2a minus 3a, which is equal to negative 3 by 2a, which is in fact what we have over here, which matches the height. This tells me that it does in fact meet at point A. Yeah, that concludes the final question of this paper. Hope you guys enjoyed and actually understood what all the concepts I included and the way you solve each question. I hope you guys enjoyed it, and feel free to share any doubts that you have in the comment section, which I'll be gladly able to clear. Do note that the paper this time is the 2020 May-June 2020 3-2 variant. Alright, and yeah, with that being said, this concludes the end of the video, and yeah, thank you for watching.